Plenty of videos already cover printed gearboxes, and some do a great job explaining how planetary gears work. But almost all of them jump straight into CAD, time-lapses the print, then keep racking weights till something fails. We'll be doing things differently instead of the usual print, snap, repeat. We'll start by analyzing forces, build a model, run simulations, and only then move to design and non-destructive testing. This approach is heavily inspired by Gabe FPV's design series. It's a different domain, but the mindset is the same, following a systematic approach, not trial and error. And if you're an engineering enthusiast, it's well worth watching. The design files are fully parametric, open sourced, and timelined, so you can follow the entire evolution and adapt it to your needs. That said, I'm not a mechanical engineer, so feedback is welcome. Before modeling geometry, we need to clearly define our requirements. What load are we trying to move and at what length? How much torque can the motor deliver optimally and under what operating conditions? What gear ratio is needed given torque, assumed efficiency, and number of stages? And finally, how much stress can our material handle? Let's address those one by one. I want to move 3 kilograms at 10 centimeters. That's a torque of around 2.9 Newton meters. I need to know the nominal torque my single stack NEMA 17 can produce under these operating conditions. Many hobbyists use holding torque as the motor's torque rating. That value is measured at zero speed with full current. It does not represent the torque available during actual motion. Always use the torque speed curve at the actual operating speed to determine the usable torque. The specs show the pull-out torque as a function of speed across different supply voltages. Operating at 30 RPM gives around 0.34 Newton meters. Based on this 2025 study, I've put the gearbox efficiency at 80%. But there's a catch. We'll come back to that. From 1 and 2, we need around 11 times the input torque. Accounting for a safety factor of 3 gives around 32 Newton meters. We'll also come back to that. Rounding up to a perfect square of 36 and splitting across 2 stages gives a final figure of 6 to 1. Formlabs tests show that PLA has a tensile strength between 50 to 60 megapascals. That's Newton per square millimeter. This 2021 study puts it between 38 to 45. Between these two resources, I picked 45 megapascals as a conservative estimate. When looking up filament strength, be careful with numbers from studies or manufacturer datasheets. There's a difference between the printed parts and raw material, and the actual strength depends on many factors. I'll be using spur gears to eliminate axial thrust, and a module of 1 to minimize size. Keep in mind that the gear module is one of our biggest knobs. Tweaking it later will drastically impact size, load capacity, and backlash. We'll come back to that. The sun gear tooth count is kept constant across all ratios to allow reuse of the same component. 3 planets strike a balance between load sharing and mechanical complexity, while the planet pins and output hub are sized around the bearings and heat set inserts I already have, using single bolt size to reduce part variety. And finally, modeling the planet pins as cantilever beams to simplify the design. The fundamental calculations are well documented online, so I'm skipping that. Now I have sun gear dimensions, planet and ring tooth relationships, planet spacing, and the basic carrier and ring geometry. With these basic dimensions, we can begin the stress analysis, covering tooth bending from the tangential loads in the sun, planet, and ring gears, radial separation forces at each mesh, stresses and deflection in the planet pins, and the combined torsional and bending loads in the output hub. I'm skipping bearing calculations. They are still and nowhere near their limits. This is really about the printed parts. All calculations are in a Python script in the repo. You'll see the symbol sigma used throughout the model. It represents normal stress, essentially force per unit area acting within the material. Bending stress is the main one at gear teeth and pins. It's typically the critical failure mode. Von Mises stress combines normal and shear components into a single value, which we then compare against the PLA limit that we established earlier within a margin of safety. Strictly speaking, von Mises isn't the best fit here. PLA behaves more like a brittle material, but it's still useful as a baseline for cross-checking simulation results. But I don't want to just pass or fail the limit. I also want to know by how much. There are two useful metrics. Utilization ratio, which is the applied load divided by the allowable capacity, and margin of safety, allowable divided by applied minus 1. The idea is the lower the utilization and the higher the margin, the better. Note how they are inversely related. It also serves as a sanity check. If sigma is very low or very high, or if margin exceeds 100, it's almost always a unit inconsistency or an equation mistake, not necessarily a bad design. Let's run the calculations. The second stage planet pin failed. That's exactly why we model first. Let's revisit the pin equation. In simplified form, bending stress scales with pin length and load, and inversely with the cube of the diameter. So here's our options. Increasing pin diameter. Doubling it increases strength by a factor of 8, but it will change planet spacing and gear meshing geometry. I'll also need bigger bearings. Option 2 is reducing the pin length, but it means the pin won't fully support the bearing, which introduces alignment and load distribution issues. Option 3 is changing the equation. Instead of a single plastic pin, we turn it into a composite beam by adding an M3 bolt. Let's update the model and rerun. Even though the pin now passes, the von Mises value actually went up. The load didn't change, stiffness distribution did. Using the single mesh backlash equation and extending it to the full planetary stage, a zero point 0.2 millimeter gear backlash gives an angular play of around 0.8 degrees. But that's only the static geometric part, the actual gap between teeth. Once you apply torque, elastic deformation takes over. Sun gear twists, carrier flexes, output shaft winds up, and even the ring gear slightly ovalizes. That deformation isn't backlash, it's compliance. Once we update the model to account for this elasticity, under 30 newtons of force, lost motion jumps to 6 degrees. At 10 centimeter radius, that's 10.5 millimeter of play. And even that's still optimistic. I've made lots of simplifications here. This is exactly why we model first. Before even touching CAD, before spending time and money, we already know this design will not be precise. Let's revisit the main equation. In simplified form, theta scales directly with gear backlash and inversely with gear's module, number of teeth, and material stiffness. In theory, we can decrease the gear backlash itself, but that goes against good DFA. It will make the gearbox harder to put together and take apart. Let's tweak the other parameters one at a time and see how the system responds. I'll also add a function to show the maximum safe load. There is a catch with this method. We'll come back to that. Here's our baseline. Let's increase the module to 1.5. Deflection drops by more than 50%, with about a 30 millimeter increase in ring diameter. But notice the load capacity more than doubles. Pushing the module even higher gives more than a 70% reduction than the baseline, but the gearbox becomes significantly larger. Increasing tooth count achieves similar deflection and size to the 1.5 module case, but with lower load capacity. Switching to steel reduces deflection by more than 85%. So let's consider our options. 1. Accept the size trade-off and design for more precision at the cost of a bulkier design. 2. Switch to a stiffer material. CNC machine steel or aluminum, trading improved rigidity for a higher manufacturing cost. Or 3. Design around it. There is no free fix here. Each option just moves the compromise somewhere else. For this prototype, I'm deliberately accepting the compliance and moving forward. The goal here isn't to build a perfect gearbox, it's to build a predictable one, by modeling the limits before ever touching CAD. In practice, the right choice depends on your application. Keep in mind that I've made many simplifications. There are also effects I haven't included that still matter, like contact stresses between gear meshes and more accurate AGMA geometry factors instead of the simplified Lewis approach, and fatigue from cyclic loading as the carrier reverses. For more demanding applications like a robot arm, you would probably spend more time on the model to achieve a higher fidelity. I followed Antal's excellent video, so I won't repeat it here. I'm using the Helical Gear Plus plugin, which did most of the heavy lifting. There is 9 Fusion files that each generate a part. Some parts will be combined, others used as is. I chose to have them separate so that the design is modular. you can change a component without affecting the whole assembly, also keeping timeline compact. The downside is that the parameters are repeated. If you change the gear ratio in one component, you have to change it in others, which violates the dry principle. A better solution would be using global parameters. Check out this video by Kevin Kennedy. The full step-by-step process for generating and combining the components is in the repo, so I won't go into details here, but feel free to check it out and ask if anything is unclear. Everything that drives geometry lives in this table: gear ratio, number of teeth, module, bearing sizes, pin diameters, as well as clearances to tweak based on your printer settings. If I change the ratio, planet tooth count updates automatically, planet diameter updates, and carrier geometry follows. Another important parameter is the ISNEMA 17 flag. It updates the design to fit either a NEMA 17 or 23. With CAD done, we can do further validation. Let's run a static FEM to see how load actually spreads and verify our calculations. First, we'll update the model to show what FEM parameters we'll use. I'm using FreeCAD Workbench 1.1. There is a tutorial by Sean Heimel from DigiKey, so I won't repeat it here. I applied the tangential and radial forces to the sun gear, using values from the second stage to capture the worst case scenario. The result shows about 11.5 microns of deflection and a peak von Mises stress of 10.4 megapascals, roughly 3% higher than our model. For the Planet gear, deflection is 13 microns with a peak stress of 13.6 megapascals, around 16% higher. Still below the 15 megapascals limit, so it passes, though the margin is tight. Note that simulation figures are consistently higher. The model relies on ideal assumptions while FEM captures real geometry and load behavior. For the carrier pins, I followed a tip from Joko Engineering Help to create a custom direction for radial force, but it got applied tangentially instead. I suspect this is due to the nuances of curved surfaces. If you have a better way of doing this, let us know in the comments. Simulating the ring and carrier crashed the solver, so I skipped them, but their utilization is well below the limit, so we are good to move on. Keep in mind that both calculations and FEM assume that the material is isotropic. The part is treated as injection molded, not FDM printed, so things like layer adhesion and voids aren't captured. And contact points aren't fixed, they move along the pressure line. Before a full print, let's do some unit testing. I printed the two carrier versions, the one with the M3 bolt support and the one without. I'll test both against the reported 7.4 kilos. I'm bumping up the wall count and orienting the part at 45 degrees to improve strength. A 90 degrees orientation would have been stronger, but it would require more supports and you will end up with an uglier finish. Check out these videos by MyTechFun and Stefan from CNC Kitchen for more info. Chop Therapy even shows you how to create fins in Fusion instead of relying on the slicer's default supports. I've created a test harness and added bearings, so the conditions are closer to the real thing. First, I tested the M3 bolt version. It handled 20 kilos, no problem. For the unsupported version, I applied 7.5 kilos, then 10 kilos, 12.5 kilos, still holding. It finally broke at 15 kilos. The part survived a lot more load than predicted. Was the model inaccurate? Let's put back the unsupported pin and disable the safety factor. It passes. If I double the load, the pin fails at 15 kilos. So should we rethink the safety factor? The model itself is reasonably accurate. But 3D prints are notoriously inconsistent. A new roll of filament might not have the same strength. A small drop in room temperature while printing can weaken the adhesion. On top of that, the test was a gradually applied static load. Realistically, the part will see shock loads and fatigue. A pin that holds 5 kilos today might snap under 3 after 1,000 cycles. Because of this, we can't treat the safety factor as a fixed number. It's a band that spans a range of uncertainties. In Shigley's stress and strength section, it's not just a buffer, it's a measure of uncertainty. But if you trust your filament and printer and are okay with failure once in a while if it means better performance, go ahead and lower it to 2. But if failure causes a heavy load to drop or destroys an expensive motor, aim for 3 plus. We now have consistent results from model, simulation, and prototype. Time to print fully. The complete assembly steps are in the repo. With the gearbox fully assembled, we can begin system testing. starting with lost motion under actual operating conditions. We saw from the model that compliance is the dominant factor here. So lost motion is not constant. It depends on both load and speed. But I'll be operating at low RPMs and low acceleration. If your application is more dynamic, it's something to keep in mind. With the stepper energized to hold position, I apply varying loads to the 10 centimeter lever arm and measure the angle with an AS5600. I then reverse the direction and take the difference. I'm using a custom PCB to minimize wiring. ESP sketch, Gerber file, and the AS5600 mount are in the repo. Using half a kilo load, the average over 3 trials is 1.6 degrees, tracking the prediction almost perfectly. At just over 2 kilos, the result increased to 6.3 degrees. Here is where the model starts to drift. 3.7 kilos gave around 10 degrees of loss. 10 degrees of loss is massive. At that level of torque, the gearbox effectively stops acting like a rigid transmission and more like a torsion spring. But our model predicted 3.8 kilograms as safe load. And this is the catch. It only took into account material stress limits. The gearbox might not be physically snapping, but it has functionally failed long before it reached its theoretical limit. And that's the difference between strength-focused design and stiffness-focused design. In reality, a gearbox is broken the moment it stops meeting your precision requirements, even if the gears are still in one piece. To bridge this gap, let's update the model with a new method that moves beyond simple material stress. It now treats angular deflection as a primary failure point. By setting a functional threshold like 2 degrees, the model finally aligns with reality, giving us a safe load that's actually usable. A common trap in every video without fail is how efficiency is measured. They load the motor till it stalls using a scale or a force gauge with and without the gearbox. Compare torques, scale by the gear ratio, and call that efficiency. Few problems with this. First of all, this measures torque at zero speed. Efficiency is the ratio of power out to power in. Power is torque multiplied by angular velocity. If the shaft is not moving, angular velocity is zero, which means output power is also zero. So at stall, you are not measuring energy transmission through the gearbox, you are measuring how much static torque the system can hold, which can still be a useful metric, sure, but in the mechanical sense, that is not efficiency. More importantly, driving a motor to stalling point forces it to draw maximum current, which may risk frying the windings. And in a stepper, you will have skipped steps well before that. At this point, you've already lost any meaningful link between commanded and actual motion. It's not a performance test for efficiency, it's a stress test for failure. Finally, efficiency is not a single universal number. It depends on operating conditions, speed, load, lubrication, temperature. Reporting a single value without specifying those variables is misleading. And instead of measuring efficiency, I want to see how accurately the stepper follows commands under load. I'll sweep across different weights and speeds, tracking the maximum position error in degrees. This gives a safe operating envelope, the maximum torque the gearbox can deliver while still keeping positional accuracy. I've chosen speeds and weights that reflect real operating conditions, while still staying within the motor's capabilities. Note that the axes use roughly logarithmic spacing to capture the nonlinearity of the system. Before we spin anything, make sure motor protection is enabled. Safety first. Never risk a fire or damaging your motor. Then I check 1.8 degree step angle, no microstepping, 2 amps max current, FOC mode, UART, board rate, and address. I connect the ESP32 UART pins to the driver and sweep past the 90-degree horizontal position where torque is highest. These are the average results over 3 trials. It tells us exactly where the gearbox hits its limits. As we move towards the high-speed, high-torque corner, positional accuracy starts to degrade significantly. At 30 RPM, even with a 3 kilogram load, we are only seeing about 2.5 degrees of error. But once we ramp up to 120 RPM, the error nearly triples. Note that I didn't use lubricant because I didn't have any, but if you're going to, and you should, be careful what kind to use. This 2024 study on the effect of mineral oil, a key component in petroleum-based lubricants like Vaseline and lithium grease, shows it fundamentally changed the mechanical properties of PLA. Even though the study found an increase in strength, That's actually a problem. A good surprise is still a surprise, an unmodeled variable waiting to change your hardware. To keep your system deterministic, look into synthetic and silicon-based lubricants. Even though PLA is not explicitly mentioned, manufacturer-provided compatibility charts indicate that these lubricants are rated as having excellent or good compatibility with every category of polymer and plastic listed. So check the datasheets explicitly say plastic safe and avoid vague multi-purpose greases. To be extra sure, test compatibility by soaking a sample print in the grease or its base oil for several days. And don't over-lubricate. I retested the Lost Motion with just half a kilo load, and it's almost doubled. Now more than 3 degrees. Under load, something yielded. The gearbox isn't just loose, it's permanently deformed. That's expected. In most mainstream 3D printing, you are working with polymers. Under sustained stress and temperature, they creep over time. That doesn't necessarily mean that 3D printed gearboxes are inherently useless. There are ways to model and mitigate that. But that's a topic for another video. This wasn't just about building a gearbox, it was about the process and letting science drive the design. Starting from specifications, revalidating your assumptions, and weighing your trade offs. That's how you make an idea work instead of relying on luck. Thanks for watching.